Using the CMMI cloud computing and big data infrastructure as a foundation, predictive analytic models could focus on a variety of dimensions that comprise the contextual and outcome regime needed to more fully understand the empirical evidence associated with CMMI adoption and usage. From all this, there would be real information on the value of the CMMI model in terms of return on investment and business value. Furthermore, the range and stability of lead assessor performance would be revealed, including ad hoc, literal compliance, and business-oriented spirit compliance. With this information, the shoemaker's children themselves could become the target for process improvement, something that is apparently needed. Software inspections lab operations, software inspections return on investment, technical debt triggers and analytics, security return on investment are but some of the predictive analytics and models that will be explored. The National Software Quality Experiment was conducted over a 10-year period from 1992 to 2002. The experiment involved software inspections and the collection of defect data. There were 157 inspection labs in which 3,324 participants were trained and conducted 3,040 inspection sessions. A total of 1,020,229 source lines of code received strict and close examination using the packaged procedures of the lab. There have been 181,471 minutes of preparation effort and 71,283 minutes of conduct time expended to detect 14,903 defects. Of these 14,903 defects, 2,512 were classified as major and 12,391 as minor. A major defect affects execution. A minor defect does not. It required 12.18 minutes of preparation effort on the average to detect a defect. To detect a major defect required 72.24 minutes of preparation effort on the average. On the average, 858.74 source lines of code were examined each inspection conduct hour. There were 2.46 major defects detected in each 1,000 lines and 12.15 minor defects. There were 4.90 defects detected in inspecting 335.6 lines per session. The preparation effort was 0.64 of conduct effort. The software inspection labs produced a return on investment of 4.5. Instances of software inspection lab results are recorded in a spreadsheet roadmap whose columns are specified and defined as shown here. Using the defined software inspection lab results as measurements, the derived metrics are calculated using the expressions shown here. Software inspections return on investment is net savings divided by detection cost. Reasoning about return on investment then is assisted by evaluating the expression. ROI is assigned net savings divided by detection cost. Net savings is cost avoidance minus cost to repair now. Reasoning about net savings is assisted by evaluating the expression. Net savings is assigned cost avoidance minus cost to repair now. Cost avoidance results from the avoidance of the higher costs occurring from deferred detection and corrections. The additional cost multiplier comes into play. M1 is the additional cost to repair multiplier for development to test major defect leakage. M2 is the additional cost to repair for test to customer use, major defect leakage. M3 is the additional cost to repair for minor defect leakage. Reasoning about cost avoidance is assisted by evaluating the expression shown here. The cost to repair now, simply the cost of defect correction, is subtracted from cost avoidance to yield net savings. Hence, reasoning about net savings is assisted by evaluating the expression shown. Continuing with the definition for reasoning about net savings, M1 for 2 to 10, additional cost to repair multiplier for development to test major leakage. M2, 2 to 10, additional cost to repair multiplier for test customer use, major defect leakage. M3, 2 through 4, additional cost to repair for minor defect leakage. Defect detection, 0.5 to 0.95. Defect detection rate for development to test. Test leakage, 0.05 to 0.5. Test leakage rate for test to customer use. C1, average cost to repair major defect. C2, average cost to repair minor defect. Technical debt is the organizational, project, or engineering neglect of known good practice that can result in persistent public, user, customer, staff, reputation, or financial cost. When adopted, technical debt becomes the hole in your canoe. Each gallon of water bailed incurs additional cost. Each gallon of water not bailed adds to the sluggishness of the operation. Technical debt has generally been used to refer to postponed or deferred work, whether by intent or by neglect. Incomplete or shoddy work extracts a persistent cost on ongoing software operations. In addition, corrective rework costs more than doing it right the first time. Technical debt is typically viewed as a problem to recover from once it has occurred. However, a better strategy is to systematically anticipate and avoid the conditions that contribute to technical debt in the first place. Technical debt is considered written off only when it is eliminated at the source, including management, engineering, and process. What are the conditioning triggers for each source? The conditioning triggers for management include prioritized goals, where schedule or cost is accorded priority over defect-free delivery. A technical debt conditioning trigger is set. Organizational levels, where the software function is separated from program management by 2 or more levels, a technical debt conditioning trigger is set. Schedule, where the number of months planned is less than the estimated month at completion, a technical debt conditioning trigger is set. Cost, where the budget at completion is less than the estimate at completion, a technical debt conditioning trigger is set. Milestone completion, where the completion schedule for any milestone completion plan date is replaced with a replanned date, a technical debt conditioning trigger is set. Headcount and effort, where overtime off the clock or personnel turnover rate is trending upwards, a technical debt conditioning trigger is set. Frequency of release, where the frequency of release is daily or weekly, a technical conditioning trigger is set. The conditioning triggers for engineering include deep domain expertise. Where deep domain expertise is not widespread on the project, a technical debt conditioning trigger is set. Software architecture. Where software architecture is not tightly coupled with middleware, operating system, and network services, a technical debt conditioning trigger is set. Requirements known. Where requirements are not fully known, a technical debt conditioning trigger is set. Technical risk, where the sources of technical risk in function, form, or fit is high, a technical debt conditioning trigger is set. Product size, where product size estimates at completion exceed product size estimates planned, a technical debt conditioning trigger is set. Complexity, where cyclomatic or essential complexity trend upward from one product release to another, a technical debt conditioning trigger is set. The conditioning triggers for process include software project management, where the software project management mode is low, a technical debt conditioning trigger is set. Software product engineering, where the software product engineering mode is ad hoc, a technical debt conditioning trigger is set. Iterative development, where incremental or iterative development of design levels and delivery stages is not used, a technical debt conditioning trigger is set. Best practices, where the use of best practices is rated low, a technical debt conditioning trigger is set. Best practices include project planning, project tracking and oversight, requirements management, configuration management, software product engineering, peer reviews, risk management, and metrics. On metrics, where metrics are not used, a technical debt conditioning trigger is set. Metrics include product size, time, effort, productivity, change, defects, complexity, release frequency, and span of responsibility. Quality assurance, where quality assurance is not in place and functioning, a technical debt conditioning trigger is set. Defect rate, where the actual defect rate, including both defect detection and defect correction, exceeds the expected, a technical debt conditioning trigger is set. The technical debt analytics are used as follows. Technical debt is a function of neglect, management, engineering, and process, where conditioning triggers for management range from M1 through M6, for engineering E1 through E6, and process P1 through P7. The conditioning trigger thresholds are considered low if the conditioning trigger set count for management, engineering, or process is equal to 2 or less. Then technical debt is assigned green. It is considered medium if the conditioning trigger set count for management, engineering, or process is equal to 3 or 4. Then technical debt is assigned yellow. For high, if the conditioning trigger set count for management, engineering, or process is 5 or more, then technical debt is assigned red. With the dramatic increase in cyberspace incidents and perceptions about the high cost of investment for security readiness and survivability, there is a need for a method to reason about and compute security return on investment. Calculating security return on investment on a regular basis will fuel the level of enterprise resource commitment to cybersecurity and will do so in a sustainable manner. Security return on investment is savings divided by cost. Reasoning about return on investment then is assisted by evaluating the expression return on investment is assigned savings divided by cost, where savings is cost avoidance resulting from resistance, recognition, and reconstitution efforts. Cost includes preparation and incident cost. Incident cost is cleanup, lost opportunity, and critical infrastructure impact. Alternate methods for computing security ROI are needed to answer questions important to the security investment decision. If the expected number of incidents is low, will the security readiness investment be recouped? For an increasing number of cyber attack incidents. What are the minimum factors needed to fully recoup security investment? Is there an equitable scheme for sharing security readiness costs among the project, for the enterprise and the government? What are the guidelines for public-private collaboration and cost sharing? There are alternate methods for computing savings and cost. Furthermore, the values that populate the terms in these expressions must be realistic, accurate, and tailored to the enterprise operation. The following methods are considered. ROI number 1, savings equals or is assigned resistance savings plus recognition savings plus reconstitution savings. Cost is assigned preparation plus cleanup plus lost opportunity plus critical infrastructure. ROI number 2, savings is assigned full cost incurred minus cost with avoidance. Cost is assigned preparation plus cost with avoidance. ROI number 3, savings equal full cost incurred. Cost equal preparation plus cost with avoidance. Here's my contact information. I would be happy to receive questions and have discussions with people on this important subject.